Hello, welcome back. In this video I'm going to go over 3 different examples of using either the definition of continuity or what we had as theorem 416, an equivalent condition. So basically, again, just continuity. The definition won't come until the very end, so that will be in the third example. The first two will focus on applying the theorem, this epsilon delta statement. And so I have recalled both here, but the one we'll be focusing on, at least for the moment, will be when we have some given epsilon greater than 0, then we're going to have the task of finding some delta greater than 0 with the following condition. So by making x close enough to a, we can make the image of x close enough to the image of a. And the close enough in the latter is less than the given epsilon. We have control with the former. So in the example, we take something simple. We already know this is continuous, but this is the point of just illustrating the theorem. We have the function x squared minus 2. We want to show that it's continuous at the point a is equal to 3. So what we're aiming for is to understand f of x minus f of a, so in that case it's f of 3 less than epsilon for a given epsilon. So I'll start this problem by going through some rough work. And then I'll come back to give a proof. This is typically the pattern that you'll find with these. You want to find some delta, and ideally at this point I would say, well, give me an epsilon, I'll give you a delta back immediately. But I can't see it immediately. I need to do some rough work to find what that delta will be. And then, when writing up my proof, I can just present that delta at the beginning. So in order to go through this, I'll go relatively quickly. So f of x is x squared minus 2 minus f of 3, so that's 9 minus 2. So the minus 2's will cancel, so we just get x squared minus 9. And we have one more simplification that we can do in this case. So x squared minus 9 is the difference of squares, so x minus 3, x plus 3, and we're hoping to be able to make that less than this given epsilon. But this factorization isn't particularly special in this case. It's very, very useful, but we have this factor of x minus 3, and the x minus this value, so a is 3, so x minus 3 is the value that we can control. So we can make this factor as small as we want. And in general, we're going to have f of x minus f of a, and essentially evaluating this at a is going to give us a root. So we're always going to have the possibility of factoring x minus 3 or x minus a, and that's going to give us the greatest amount of control that we have over the expression. So just expanding that a little bit, we have the absolute value of x minus 3, the piece we have perfect control over, but then we have the other bits, and in this case the other bits are just x plus 3, and we're hoping to make that less than epsilon. So I can control this, I can make this as small as I want. But then this value over here, well, it's not x minus 3, it's x plus 3. So essentially, as x is getting close to 3, this term is going to 0, so that makes this whole thing small. But as x is going to 3, this value here is somewhere around 6. And so very roughly, as x minus 3 goes to 0, x plus 3 approaches 6. So this is certainly true, but of course this isn't precise. This isn't finding a given delta. So what I need to work with is precisely the condition that I have. X minus 3 is less than delta. So if x minus 3, absolute value, is less than delta, then x is an element of 3 minus delta, the open interval, up to 3 plus delta. And consequently, this x plus 3, I'll move this up in a moment, is an element of 6 minus delta, so I'm just shifting everything 3 to the right, 6 plus delta. This is where I have the first real choice. So I'm choosing delta, it's going to be based on epsilon. But I need to be able to control the size of this product. And x minus 3, that's fine, I can deal with that. The x plus 3, I don't want it to be too big. I want to make sure that I can control how large this gets. And as large as this might get, it must be compensated by how small x minus 3 can get. So this x plus 3, my 6 minus delta, so I'm thinking of delta as being small, but in absolute value, in either case, 6 minus delta will be smaller than 6 plus delta, since delta is positive. And so what we have is x plus 3 is going to be less than 6 plus delta. So I'm going to make a fairly just arbitrary choice and say that if delta is less than 1, then the absolute value of x plus 3 is less than 7. And I've just chosen 1 just to keep things simple. So with that, it's an assumption, but it's an assumption I can make. The original inequality becomes x minus 3, x plus 3. So that's the quantity that I want to make less than epsilon. I now know that x plus 3, I can make this less than 7. So this is less than 7 times x minus 3. And for this to be less than epsilon, so this is what I'm aiming, I don't know this already. For this to be less than epsilon, we need that the absolute value of x minus 3 is less than epsilon over 7. And so in order to satisfy that, well, we could take delta to be epsilon over 7. Now that might not sit very well with my delta as something less than 1. If epsilon is bigger than 7, then taking epsilon over 7 will be bigger than 1. So we take both of those into account, and we take delta to be some real number less than the minimum, less than because I have a less than over here, less than the minimum of 1 and epsilon over 7. And in order to write this down as a proof, I need to go through basically what I've done already, but go through backwards. So essentially stating for my given epsilon, I have this delta, and then proving that it gives me what I want. So I make a claim. I claim that the function is continuous at the given point. And so to prove this, using the theorem that I want to use, I take epsilon greater than 0, so this is any, so that epsilon will be greater than 0, and I take my value of delta. Now I have it over here, set delta such that delta is greater than 0, but it's also less than the minimum of 1 and epsilon over 7. So with this information, I study f of x minus f of a. So then minus, so essentially I'm going through the same things I had before, but now I have this delta that I'm going to use to simplify the inequality all at once. And this is where the knowledge of what I've done previously comes into play. So we know that this is less than 7 times x minus 3. So I'll put a little note here because I want to justify this. Right now it's true because of the work I've done before, but I haven't justified it within my proof. And then that in turn, and that requires a little extra justification, is less than 7 epsilon over 7, which is equal to epsilon. And so justifying these two inequalities, 1 and 2, will be enough to then complete the proof. So 1 is looking at the inequality involving the absolute value of x plus 3. So we can examine that inequality in the way that we had. So x plus 3, that is equal to x minus 3 plus 6, and then that is less than or equal to x minus 3 plus 6, or plus the absolute value of 6. And so this is by triangle inequality. But now I know something about x minus 3, which is that this is less than delta. So in turn, this is less than 1 plus 6, and this is, since x minus 3 less than delta, and delta is less than 1. And so indeed that is 7, so that gives me the inequality. And 2 holds more directly. Maybe it's fairly trivial at that point, but we're saying that absolute value of x minus 3, well, absolute value of x minus 3 is given to less than delta, I'm assuming that. and delta is less than epsilon over 7. So that gives me the inequality, and the proof is valid. Actually, just looking at it, I'm not entirely clear when I've been assuming that x minus 3 is less than delta. So set delta such that, and then I really should have had up here the absolute value of x minus 3 is less than delta. And then everything else will go through just fine. Okay, in this example, I'll forego the proof at the end. So I'll do the rough work, but then the proof is assembled in much the same manner. So here we have something which is not a polynomial, rational function instead. And we want to show that it's continuous at some a is equal to 1 using the same condition that we had previously, the same epsilon delta condition. So for that, we take epsilon to be greater than 0, and we want to find a delta. So we want to find delta greater than 0 such that x minus, in this case 1, less than delta implies f of x minus f of 1 in absolute value is less than epsilon. So for the rough work, I'm going to continue to focus on this, and from that get some information about what my delta can be, and then I would use that in a proof, and I would set that out from the beginning of the proof. So plugging everything in, we have 1 over 1 plus x squared minus 1 over 1 plus 1 squared. So this becomes, so this is 1 over 2. So we have 1 minus x squared, so this will be absolute value, over 2 times 1 plus x squared. And so just like before, we have this information about the absolute value of x minus 1. And we're going to be able to find a factor of x minus 1. Within this, we have this 1 minus x squared. So let me write that over here for convenience. And so 1 minus x squared, or x squared minus 1, absolute value means I don't really care about which order. This is going to give me a factor of x minus 1. They will also give me a factor of x plus 1. And finally, I'll have a factor of this 1 over twice 1 plus x squared. So now we have three things. So the first one we have absolute control over, and so essentially I will look at this last. X minus 1 is less than delta, so we have that indeed. And the other two are where I can have something to worry about. So I worry case by case. In the first case, so this x plus 1 factor, we have that as x is getting close to 1, as x minus 1 is less than delta, x lies essentially within delta of 1. So it's 1 minus delta up to 1 plus delta. So if I do something similar to before, take delta to be 1, then this will lie somewhere between 1 and 3. So let me just write that down in detail. So as x minus 1 is less than delta, we have that x is an element of 1 minus delta, 1 plus delta. And that in turn tells me something about x plus 1, which is that x plus 1 lies in 2 minus delta up to 2 plus delta. And so if we were to take, and again, this is, as before, this is an assumption. I have control over delta, so I'm able to make this assumption. But if delta lies between 0 and 1, that implies that the absolute value of x plus 1, again, this isn't really a proof. This is just my rough work. So the absolute value of x plus 1 is less than 3. It's true, so that's fine. Now, the next case, so this expression here, we have 1 over 2 times 1 plus x squared. And again, we have the same thing because we still have x minus 1 less than delta. So we have, again, x is an element of 1 minus delta, 1 plus delta. And if I reuse the same assumption, so that 0 is less than delta, less than 1. I'm reusing it at this point just because I know it's going to work out a little bit more clearly in this case if I put that in here. So in that case, x is an element of 0 to 2. X squared, because that's what's featuring here, is an element of 0 to 4. And then we have a 1 plus x squared is an element of 1 up to 5. And so all told, as long as 1 plus x squared is an element of 1 to 5, maybe I want to account for the 2 as well, so I can include that, although I can just more or less read that off. So this denominator lies between 2 and 10, so in total 1 over 2 times 1 plus x squared. So absolute value or not, it doesn't really make any difference in this case. This is an element of 1 over 10, 1 over 2. So note that because I'm taking a reciprocal, everything has flipped. So we have a lower bound of 1 over 10, upper bound of 1 over 2. So in particular, after all that work, we get that the absolute value, with this assumption that delta is less than 1, this is less than 1/2. Now the thing is, that's a little foolish. All I really care about is a bound. It's not that this work is wrong. It's certainly true that 1 over twice 1 plus x squared is less than 1/2. But I can get that much more easily. So if I just look at the expression again, first thing I can note is that x squared is greater than or equal to 0 for any value of x. So twice 1 plus x squared is greater than or equal to 2. And because I'm taking a reciprocal, we get that this expression, 1 over twice 1 plus x squared, is less than or equal to 1/2. And indeed it's always positive. So in absolute value it's less than or equal to 1/2. And I didn't have to go through any of these steps. And maybe this would have resulted in a larger bound. Maybe I would have had a bound of 1 here. I didn't, but so be it. I really just care about a bound. So whatever is the easiest way to justify a bound, that's going to be the better way to approach the problem. Now at that point I've controlled everything. So I know, let me just account for it up here. So this x plus 1 is less than 3. So that's less than 3. And then this is less than, well, I have 1/2. It could be less than 1, it could be whatever. So it's less than 1/2. That's the bound I've justified. So in total, this is 3 over 2 delta. And I want this to be less than my value of epsilon. So what I'm going to take is such a value of delta, so less than 2/3 epsilon. And of course I can't forget that I've used some information already, some assumptions about delta, actually twice now. So I have to take it to be less than the smallest of these values. So less than 2 over 3 epsilon, or 1. And this 2 over 3, I don't necessarily need to carry exactly that, but any bound that works is going to be fine. So now that I have my delta, I can actually sit down, I can write a proof, although I leave that as an exercise in this case. Okay, so I'll end with an example from a past exam paper. But this is an example that I want to give because I can use the definition of continuity that we had involving sequences. So the condition here is that if you take a real function, so function from the reals to the reals, it's the identity function if the input was a rational number, and it gives me 1 minus that value if it's an irrational number. And so the question is to show that f is continuous at only one point. In fact, the question, as stated on the exam, is to show that it's continuous when a is equal to 1/2 and discontinuous otherwise, so not continuous otherwise. So just to give a quick indication of this, if you take a graph of the function, and of course I can't perfectly draw this graph because the rationals are dense within the reals, between any two real numbers there's another rational number. So the best that I can hope for is that I draw a point above every rational, and on a board that's just going to look like a straight line. So when I draw this straight line, I really just mean for x a rational number. On the other hand, if I take the other side of the function, so taking irrational values, looking at 1 minus x, again, it's dense within the reals. So I'm going to end up with the function, it'll have 1 here, and it'll cross this way. And so that's x, let's just say not a rational number. And so what we have is this value that's going to happen when a is equal to 1/2, where the two graphs intersect. And it's at that point that it's going to be continuous. So when we have a problem like this, we can break it largely into two parts. So we show that f is continuous at a is equal to 1/2, and show that it's discontinuous elsewhere, although that will have two parts as well, because we have discontinuous at some other rational number, or indeed discontinuous at an irrational number. So in order to prove this, I'm going to use the sequential definition. And so let's just say if you take any sequence which converges to 1/2, so converges to this a, if I can show that the resulting sequence f of xn converges to f of a, so in this case f of a, that's equal to, I should be clear, yeah, I do have a is equal to 1/2, f of 1/2, 1/2 is rational, so it just gives us back 1/2. So I need to show that f of xn converges to 1/2. To do this, I take the absolute value of f of xn and subtract what I hope to be the limit, 1/2, and then I can evaluate this. And it's going to split into two cases because the function splits into two cases. So either xn is rational, so we just get xn minus 1/2. That happens if xn is a rational number. And if xn is irrational, then instead of xn, we'll see 1 minus xn minus 1/2. So that's xn irrational. But of course, the thing to point out here is that 1 minus xn minus 1/2, rather I should have absolute values, but this 1 minus xn minus 1/2 is just going to be 1/2 minus xn. So this is equal to 1/2 minus xn. And this is the very same, because I'm taking absolute values, xn minus 1/2 is identically 1/2 minus xn. So simplifying this, the absolute value of f of xn minus 1/2 is equal to xn minus 1/2, the absolute value of that. So this doesn't care whether it's rational or irrational. And so we can use that xn converges to 1/2 to show that f of xn converges to 1/2. And indeed that was equal to f of 1/2, and so that will be part A complete. So then part B. So this is to show f is not continuous at a not equal to 1/2. And so this pins on two different ideas. So recalling the definition of continuity, any given sequence converging to my value of a must give me a new sequence, f of xn, if that was the sequence, converging to f of a. And so if that must be true for every single sequence, in order to show that something is not continuous, or to show that it's discontinuous, I need to give only one sequence. So in other words, give a counterexample. So that is a sequence xn which converges to a, but for which f of xn does not converge. And this doesn't mean it converges to something else, it might just not converge, but it does not converge to f of a. So there are maybe two subcases. First of all, if a is rational, and indeed a not equal to 1/2, this was excluded up here, then any sequence such that xn converges to a and xn is not a rational number for all n, this will work. And it's not difficult to write down such a sequence. We could simply say xn is equal to a plus pi over n, or take your favorite irrational number. There's a few details left, which can be left as an exercise. And then in the final case, if a is irrational, then any sequence xn converges to a, but xn is a rational number. So one example you can take, if a is an irrational number, then maybe xn are the value of a up to n decimal places. I wanted to end with essentially a bonus exercise. So as I went through some of the past exam papers, I picked on May 2016 because it had a nice example of something we could do with a continuous function, something we can do with a sequence definition more readily than the epsilon delta. But part of that question, separate from the previous part, also connected the concepts that we've seen in series together with the concepts that we're just working on now with continuity. So I think this is a nice problem. I won't go through the solution here. This is something we can discuss in a different environment. But nevertheless, we have everything we need to solve this problem already. And really, it's getting to the heart of trying to understand continuity and understand something about a series and how we will prove convergence of the series. There is perhaps only one thing that I'll note. We're not saying that the sequence xn by itself converges directly. We're saying something about the series, the sum of f of xn, and something about the function, of course, f of x. But now for a genuine end.